Practice 1. Matter, atoms, elements, compounds, and mixtures. Look at the 4 particle diagrams. The question is asking us to classify each diagram as an atom, an element, a compound, or a mixture. Diagram A shows single particles that are not bonded to anything else, so this represents atoms. More specifically, these are separate atoms of the same type. Diagram B shows particles bonded in pairs, but all the particles are the same type. So this is an element. It is still an element because only one type of atom is present. Diagram C shows 2 different types of atoms chemically bonded together. The same bonded particle is repeated, so this is a compound. Diagram D shows more than one type of particle in the same box. Some particles are single atoms and some are bonded molecules. So this is a mixture. The key idea is this. An element contains only one type of atom. A compound contains different atoms chemically bonded. A mixture contains more than one substance that is not all chemically bonded together. Practice 2. Filtration. In this question, we have a mixture of sand and water. The mixture is poured through filter paper. The purpose of filtration is to separate an insoluble solid from a liquid. Sand is insoluble in water. That means it does not dissolve. Because the sand particles are too large to pass through the tiny holes in the filter paper, they stay on the filter paper. The solid left on the filter paper is called the residue. So in this case, the sand is the residue. The water can pass through the filter paper and collect in the flask below. The liquid that passes through is called the filtrate. So in this case, the water is the filtrate. This method works because the 2 substances have different physical properties. The sand is an insoluble solid, while the water is a liquid that can pass through the filter paper. Practice 3. Evaporation and recrystallization. This question is about purifying an impure soluble solid. First, the impure solid is dissolved in a small amount of hot solvent. Hot solvent is used because many solids dissolve better at higher temperatures. Next, the hot solution is filtered. This removes any insoluble impurities that did not dissolve. After that, some of the solvent is evaporated. This makes the solution more concentrated. Then the solution is allowed to cool slowly. As it cools, the pure solid becomes less soluble and begins to form crystals. The crystals are then collected by filtration, washed with a small amount of cold solvent, and dried. Cold solvent is used for washing because the crystals are less soluble in cold solvent. This helps remove impurities without dissolving too much of the product. So the main idea is solubility. The solid dissolves in hot solvent but crystallizes out when the solution cools. Practice 4. Simple distillation. This question asks how simple distillation can be used to obtain pure water from seawater. Seawater contains water and dissolved salts. The salts are non-volatile, which means they do not easily evaporate. When the seawater is heated, the water reaches its boiling point and changes into vapor. The dissolved salts remain in the boiling flask because they do not evaporate with the water. The water vapor travels into the condenser. Inside the condenser, cold water flows around the tube and cools the vapor. The vapor then condenses back into liquid water. This liquid is collected in the receiving flask. The collected liquid is called the distillate. In this case, the distillate is pure water. So simple distillation works because water can evaporate and condense, while the dissolved salts stay behind. Practice 5. Reflux. This question asks why reflux is used when a reaction mixture needs to be heated for a long time. In reflux, the reaction mixture is heated in a flask. As the mixture is heated, some solvent or volatile reactants may turn into vapor. The vapor rises up into the condenser. The condenser is cooled by water flowing through it. When the hot vapor touches the cold surface inside the condenser, it cools down and condenses back into liquid. The liquid then drips back into the reaction flask. This cycle happens again and again. Vapor rises, condenses, and returns to the flask. Because of this, the reaction can be heated for a long time without losing much solvent or volatile reactant. The important idea is that reflux allows prolonged heating while keeping the total volume of the reaction mixture nearly constant. Practice 6. Separatory funnel. This question is about separating oil and water using a separatory funnel. Oil and water are immiscible liquids. This means they do not mix together. Instead, they form 2 separate layers. The denser liquid forms the lower layer, and the less dense liquid forms the upper layer. Water is denser than oil, so water forms the lower layer. Oil is less dense, so it forms the upper layer. To separate them, the mixture is placed in the separatory funnel and allowed to settle. Then the tap, or stopcock, is opened. The lower water layer is drained into a beaker first. The tap is closed before the oil reaches the opening. Now the water and oil have been collected separately. The key point is that a separatory funnel separates immiscible liquids because they have different densities and form separate layers. This question compares two solid samples, P and Q. Sample P melts sharply at 122 degrees Celsius. Sample Q melts over a range from 115 degrees Celsius to 121 degrees Celsius. A pure substance usually has a sharp and fixed melting point. This means it melts at one specific temperature or over a very narrow range. An impure substance usually melts over a wider temperature range. Impurities disrupt the regular arrangement of particles in the solid. Impurities also usually lower the melting point. So sample P is more pure because it has a sharp melting point at 122 degrees Celsius. Sample Q is less pure because it melts over a range of temperatures. The broad melting range shows that impurities are present. So when we use melting point to judge purity, a sharper melting point usually means a purer substance. Practice 8. Paper chromatography. This question asks how paper chromatography separates the components of a mixture. In paper chromatography, the paper is the stationary phase. It does not move. The solvent is the mobile phase. It moves up the paper by capillary action. The mixture is placed on the origin line. As the solvent moves up the paper, it carries the substances in the mixture with it. Different substances move different distances. A substance that is more soluble in the solvent will move further up the paper. A substance that is more strongly attracted to the paper will move a shorter distance. So separation happens because the components have different solubilities in the mobile phase and different attractions to the stationary phase. In simple words, some components travel further with the solvent while others stay closer to the paper. This creates separate spots on the chromatogram. Practice 9. Kinetic molecular theory and states of matter. This question asks us to explain solids, liquids, and gases using kinetic molecular theory. Kinetic molecular theory says that matter is made of tiny particles, and these particles are always moving. In a solid, the particles are closely packed in fixed positions. They cannot move freely from place to place. They only vibrate around fixed points. This is why solids have a fixed shape and a fixed volume. In a liquid, the particles are still close together, but they can move past one another. This is why liquids have a fixed volume, but they can flow and take the shape of their container. In a gas, the particles are far apart. They move rapidly and randomly in all directions. This is why gases do not have a fixed shape or fixed volume, and they fill the container. So the differences between solids, liquids, and gases come from particle spacing, particle movement, and the strength of attractive forces between particles. Practice 10. Heating curve and changes of state. This question asks why the temperature stays constant during melting and boiling, even though heat is still being added. On a heating curve, the sloped parts show temperature increasing. During these parts, the particles gain kinetic energy and move faster. But during melting and boiling, the graph becomes flat. The temperature does not increase. This is because the energy being added is not used to increase kinetic energy. Instead, the energy is used to overcome intermolecular forces between particles. During melting, energy is used to loosen the particles from their fixed positions in the solid. During boiling, energy is used to separate particles so they can become a gas. Because the average kinetic energy does not increase during the phase change, the temperature remains constant. So the main idea is this: during a change of state, added energy changes the arrangement of particles, not their temperature. Practice 11. Maxwell-Boltzmann distribution. This question asks what happens to a gas sample when it is heated from temperature T1 to a higher temperature T2. At the higher temperature, particles have greater average kinetic energy. This means they move faster on average. On the Maxwell-Boltzmann distribution, the higher temperature curve becomes lower and broader. The peak of the curve shifts to the right. This shows that the most probable speed has increased. The curve also spreads out more because there is a wider range of particle speeds. A greater proportion of particles now have high kinetic energy. However, the total area under the curve stays the same. This is because the total number of particles has not changed. So the important points are lower curve, broader shape, Peak shifted to the right and more particles with higher speeds. Practice 12. Temperature and particle energy. This question asks about the relationship between absolute temperature and the average kinetic energy of particles. Absolute temperature means temperature measured in Kelvin. As temperature increases, particles move faster. When particles move faster, they have greater kinetic energy. So the average kinetic energy of particles is directly proportional to absolute temperature. This means that if the temperature in Kelvin increases, the average kinetic energy also increases. Kelvin must be used because it is an absolute temperature scale. It starts at 0 Kelvin, which is absolute zero. At absolute zero, particle motion is at its minimum possible value. Celsius is not suitable for this direct relationship because 0 degrees Celsius is not the point where particle motion is at a minimum. So the key idea is simple. Higher Kelvin temperature means higher average kinetic energy. Lower Kelvin temperature means lower average kinetic energy.